Warm welcome. Thank you for joining. Grab a notebook, pen or pencil, whatever you want to write with is fine. This is math from the void. Math coming at you out of nowhere. So today we have a problem from the 2007 Calculus BC exam. Part C requires a technique that you learn in BC called integration by parts. So AB students, if you're listening, tuned in, you can do parts A and B, but part C would be very difficult unless you have this technique down from Calc 2. Okay, so take the time to pause the video, give yourself a moment to try to work on this problem. Give yourself about 12 minutes or so, and then come back and join us. Let's get started. They give us a function defined for x greater than 0 with an initial condition, and the derivative is given by x squared, ln of x. So we know that there's this point on the curve, e comma 2, and you can plug it in for yourself and you would see that. Actually, we don't have the original function yet, so I guess you couldn't see that. We have to take it for granted now that we have a f of e equals 2. Part A, they want us to write an equation for the tangent line, so let's bust out the equation. Y minus y value equals m times x minus x value. That's the equation of the point slope form for a line, and we already have the x and y value, so we really don't have to do that much work, honestly. We just have to plug in the slope. How do we find the slope? Well, that's what the derivative does. So let's go ahead and plug in e to the slope, and that's going to give us e squared times ln of e, which is just going to be e squared times 1, which is e squared. So that is the slope. And we can plug in our points. Y minus 2 equals e squared, parentheses, x minus e. All right, it's a perfectly valid equation for the line. You don't have to get it into y equals mx plus b format, slope-intercept format. Part B, is the graph of f concave up or concave down on this interval? So they're asking about the second derivative now. They're asking if second derivative is positive or negative, basically. Is it greater than 0 or less than 0? So we need to find out what is the second derivative. This is going to be the derivative of a product. We have x squared times ln of x. So the derivative of a product, how do we do that? Take a derivative of the first thing, leave the second, plus leave the first thing, derivative of the second. So these are pretty easy derivatives. 2x ln x plus x squared and then times 1 over x. So we can simplify this a little bit. 2x ln x plus x. That's good enough. If you want to simplify it by taking out x, I mean, you can, but you really don't have to. Really, we just want to check what's going on here. Actually, it could be a good idea to factor because we want to see what's going on here in terms of negative or positive. And it could be a good idea to just plug in 1 and kind of see what's going on there. That would be 2 times 1 times ln of 1, which is 0, plus 1. So we get 0 plus 1. That's a positive. Okay, that's worth noting. And then what about double prime of 3? Now this is definitely still going to be positive, right? Because both of these functions are increasing now that I think about it. So they're only going to get larger. So if you plug in a bigger number, you're going to get a bigger output. 2 times 3, and then times ln of 3 plus 3. This is, I don't know, it's approximately 10, almost 10. So we know that it's positive the whole time. That's kind of worth noting, but in case you wanted to be really precise, let's put this on a chart really quickly. If we factor this as x times 2 ln of x plus 1, then we can have our factors written as such. X 2 ln of x plus 1. When does 2 ln of x plus 1 equal 0? When would this possibly equal 0? That would be e to the negative 1/2, which is 1 over the square root of e. That's when this would be 0. And as long as x is positive, which it does say in the domain, of course our x is just going to be positive. So the question is 1 over e, 1 over square root of e. That's less than 1, right? Because our interval that we're interested in is from 1 to 3. So far it looks like that's positives. Yeah, as long as this 1 over square root e is less than 1. And it is, because e is bigger than 1, so the square root of e has to be bigger than 1. You don't have to know what it is, but it's bigger than 1. So if we do 1 divided by square root of e, right, basically if we divide both sides by square root of e, then we're going to get 1 is greater than 1 over square root of e. Okay, so that's just kind of confirming what we already checked, that the second derivative is positive. So we would say f is concave up on the interval 1, 3, and that's because f double prime is greater than 0 on that interval. Okay, part C is where we have to use Calc BC with Calc 2 technique, which is integration by parts. This is basically the product rule for integrals, if you want to think of it like that. What do we have here? We want to use the antiderivative of f prime, and using the fundamental theorem of calculus, that means we're going to have f of x plus c. Cool. So it's all just about, basically just a matter of taking the antiderivative of this product. We have to make a selection for dv, and we have to make a selection for u. Using what I call the detail model, we're going to want to pick u to be ln of x. And dv is going to be x squared dx. Okay? So now that means du is just going to be 1 over x dx. And v is going to be the integral of x squared, which is 1/3 x cubed. Nice. So we can express this using the integration by parts formula. It's going to give us 1/3 x cubed ln of x minus integral of v du. It's 1/3 x cubed times 1 over x dx. This will simplify as 1/3 x squared dx. And this part we can take an antiderivative of. This is a super easy antiderivative. This is just going to be, due to the power rule, 1 over 9x cubed. And of course, you can always check your antiderivatives. How? By taking a derivative. If you have time, you can take a derivative of this, and it should simplify to what we started with, x squared ln of x, right? So in fact, I want you to get used to doing that. If we were to do that, we have a product here. What's the derivative of the product? Take a derivative of the first one, leave the second, plus leave the first one, take a derivative of the second. So this would be just x squared, and leave ln x. I can already see where this is going. The 3 times the third canceled, plus leave the 1/3 x cubed, and then take a derivative of ln of x, which is 1 over x. And then we're going to subtract the derivative of 1/9 x cubed, which is going to be 1/3 x squared. And I don't know if you notice it, but this is positive 1/3 x squared, and this is negative 1/3 x squared. So those will cancel, leaving us with just x squared ln of x. So it's never a bad idea to check. Let's find the exact function f of x. We do have an initial condition that we can use to find the plus c. So this is f of x, but it's f of x plus c right now. So let's plug in e. It's going to be 1/3 e cubed times ln of e, that's always nice, minus 1/9 e cubed plus c equals 2. So this is 1/3 e cubed minus 1/9 e cubed. Maybe I should just call this 3/9 e cubed. Okay, 2/9 e cubed plus c equals 2. So there's our kind of peculiar c value. And now we can write out the full function as just f of x is 1/3 x cubed ln x minus 1/9 x cubed plus 2 minus 2/9 e cubed. That is our final answer for the function. So, pretty easy problem, to be honest. If you understand integration by parts, the last part should be pretty smooth. If you don't understand integration by parts, okay, part C probably wasn't very smooth, but I think the others were completely clear. A and B is just basically using the derivative to write a tangent line, which they already gave you a function for the derivative, and then using the second derivative in part B. Yeah, comes in handy to use a chart. You don't always need it. In this problem, I don't think you particularly needed it, but everything was calculated by hand. There was nothing that you needed to get unexpected decimal value or something like that. So leaving everything in terms of e is fine. Worked with a little bit of fractions. That was pretty much it. We even had time to spare to take the derivative of our function to make sure that it gives us the f prime we started with. So yeah, very approachable function. All right, that's enough blab out of me. I'll see you guys next time in the void.